Hello everyone. Welcome to a new lecture in the series of data-driven model predictive control. So far in this lecture series, we were discussing different approaches in data-driven linear MPC. From this lecture onwards, we will be shifting the focus to nonlinear MPC, where we discuss the conventional nonlinear MPC in this lecture and the data-driven nonlinear MPC approaches from next lecture onwards. Here is the overview of this lecture. We will be starting with the output-based nonlinear MPC. Then we move on to the state-based NMPC. In the output-based nonlinear MPC, we will be using the output information or the predicted output data for computing the MPC control law. Here, we will be using a discrete time nonlinear system for predicting the state and output. And this nonlinear model can be represented as in equation number 1, in which k is the discrete time instant, xk is the state vector at the time instant k, uk is the control input vector, yk is the output vector at the time instant k. Here, this f and h are the nonlinear functions which represent the state dynamics and output dynamics. In the conventional NMPC, this f and h are assumed to be known. In other words, the structure and the parameters in this f and h will be known. Therefore, we can use these functions for predicting the state and output data. The constraint sets used for this MPC are defined as in equation 2, where we define the state, input, and output constraints as linear inequality constraints. Similar to the output-based LMPC, here we will be defining the cost function for the output-based NMPC as in equation number 3, in which we have a output error term and control error term, which are summed over the prediction horizon. The output-based NMPC problem can be defined as in problem 1, where we will be considering a nonlinear system and the current and output is assumed to be known. And the objective is to compute the control input sequence UK, which minimizes the cost JY subjected to these constraints. These equality constraints are defined using the nonlinear model, which is assumed to be known. Now, using the nonlinear model, we can compute the predicted state and output sequence as in equation number 5, where xk plus 1 given k equal to f of xk given k uk given k, and yk plus 1 given k is equal to h of xk plus 1 given k. And by recursively applying this equation, we can compute all the predicted states and the output over the prediction horizon. And here we compactly represent this equation using a function fyp. Now using this predicted output sequence and control sequence UK, we can rewrite the cost function for output-based NMPC as in equation number 6. The output and input constraints can be rewritten as in equation number 7. The optimization problem for output-based NMPC can be represented as in equation number 8, where the cost function will be a nonlinear function of the input sequence UK, and we have to minimize this cost function subjected to these constraints. The constraints are also a function of the input sequence UK. Here the cost function and the constraints are nonlinear functions of the input sequence UK. Therefore, this will be a nonlinear programming problem and which can be non-convex. This makes the optimization problem for output-based NMPC more challenging compared to the LMPC setting, where the optimization problem was a QP and convex. Next, we move on to the state-based NMPC, and here the only difference is that the cost function will be defined using the predicted state instead of output. And similar to the LMPC setting, we can define the cost function for the state-based NMPC as in equation number 9. And here we will be having a state error term and a control error term, which will be summed over the prediction horizon. In the state-based NMPC problem, the objective is to compute the control input sequence UK, which minimizes this cost function JX and subjected to the constraints. Now, using the state function f, we can compute the predicted state sequence as in equation number 11. It can be compactly represented as fxp of xk given k, uk, and using which we can represent the cost function for state-based NMPC as in equation number 12. Similarly, we can rewrite the state and input constraints using the predicted state sequence as in equation number 13. Then the optimization problem for state-based NMPC can be represented as equation number 14, where we have to compute the optimal controlled sequence UK, which minimizes this cost function subjected to the state and input constraints. And here also the cost function will be a nonlinear function of the input sequence UK, and the constraints are also nonlinear inequality constraints. Therefore, this optimization problem will be nonlinear programming problem, which will be normally non-convex. In the next lecture onwards, we will be focusing on data-driven nonlinear MPC, where we consider the model of the system is unknown, and we will use the input and output data for computing the MPC control law. That leads us to the end of this lecture. Thanks for watching.